Hello, in this lecture we are going to talk about proportionality problems. What are those really? The objective of proportionality problems would be to use algebra and physics together. So we use some physics concepts and along with algebraic methods to make physical comparisons. So in this lecture we are going to examine some examples for proportionality problems, but in the context of 1D kinematics that we have already learned so far. However, we'll meet proportionality problems in every other chapter that we study, because this is really an algebraic method that can be used with any other physics concepts. Okay, so let's say we have an equation x equals 1 over y squared. Now we want to know what happens to x if y is tripled. Okay, so what is that? How do we solve that? Y is tripled. That means y is now changed to 3y. Okay, so we call this new y prime is equal to 3 times of y. Okay, so y prime is the new y, which is equal to 3 times of old y. Then, according to this equation, x will be now a new x, call it x prime. So, which will also have a new equation like x prime equals 1 over y prime squared. Okay, so wherever you see y prime, you'll replace it with 3y. So x prime is equal to 1 over 3y whole squared. Alright, then that means x prime is equal to 1 over y squared times 3 squared is 9, so 1 over 9. Now 1 over y squared, what was that? 1 over y squared was in fact equal to x. So this is actually x, the old variable. Therefore, we have the new x, that is, this is how x has changed. X prime has, the new x has become x prime, which is equal to 1 over 9 times the old x. So x has decreased by a factor of 1 over 9. Okay, let's now examine a different example, but with the same equation. So we still have x equals 1 over y squared as our given equation, but now we flip the question saying we want to know what happens to y if x is increased by 60%. So we are increasing x by 60%. And we want to know what happens to y. So what is actually different about this problem? In the previous problem, we wanted to find how x changed with respect to a change in y. So we didn't need to rearrange the equation. Now we want to see a change in y. So we have to make y the subject of this equation. Or in other words, we have to solve for y first to make it easier for us to examine. So let us rearrange this equation and solve for y. Here we have given x equals 1 over y squared. Cross multiply x to y squared and 1 to 1 down here. So xy squared is equal to 1. And then that means y squared, divide both sides by x, gives you 1 over x, and so y is actually square root of 1 over x. So square root of 1 is still 1, square root of x is we don't know. So our new equation is y equals 1 over square root of x. Alright, the question tells us that x has increased by 60%. That means whatever x was in the beginning, it is now 60% more. So x has gone to a new x, which is we call x prime, which is equal to an increased form of the original x. What is the increased number? The increment number is the original percentage, is 100%. So 100 over 100. To that we add or increase by 60%, which is 60 over 100. This gives you 1 and this gives you 0.6. So this in total becomes 1.6 times x. So x prime is equal to 1.6 times x. We want to know what is y prime. Okay, y prime is the new y with respect to the new x, which is x prime. We use the equation given here. So using y prime, we have y prime equals 1 over square root of x prime. What is x prime? X prime is nothing but 1.6 times x. So y prime is equal to 1 over square root of 1.6 times x. All right. So let's go down here. 1 over y prime is equal to 1 over square root of x times 1 over 1.6. All right. So what is 1 over square root of x? 1 over square root of x is nothing but y. So y prime is equal to whatever 1 over square root of 1.6 is times y. Okay, that means y has changed by a factor of 1 over square root of 1.6. Now let's look at an example which focuses on kinematics, okay, and use proportionality to determine the answer. What does the question say? So in the question we have two tennis balls which are dropped from the same height into two separate deep wells. The first ball takes 5 times as long as the second ball. So this is our proportionality relation. There are two deep wells. 2 tennis balls are dropped into each. The first ball dropped into the first well takes 5 times as long as the second ball dropped into the second well to reach the bottom of the wells. How much deeper is the first well than the second well? We want to find the proportionality factor of how much deeper the first well is compared to the second well. Okay, so for example, if second well was x, first well would be some factor multiplied by x. That is what proportionality factor is. Let's work out the solution to this problem. We want to first be able to note down the relevant variables in a very organized manner so that we don't get lost in the problem. First, let's look at what our target variable is. We want to know how much deeper is one well from the other. So the target variable is some kind of displacement, okay, the displacement that the tennis balls are covering. So our target variable is delta y. All right, now what are we given? We are given information about 2 wells. Let's break them down into columns. Well 1 and well 2. Okay, all right then. Now, what other information do we know from the beginning? We know that the balls are dropped from the same height, okay? So when a ball is dropped, the initial velocity is 0 meters per second because initially the balls are at rest and then you just release it. So the initial velocities of both the balls is 0. So let's call it 1 and 2. All right. Also, we know that acceleration is negative 9.8 meters per second squared, right? Because as the ball is falling, and we usually denote upward to be our positive y direction. So the acceleration is always downwards due to gravity, which is why it is negative. So acceleration is the same in both cases. Okay, then what? T1, T2 are the times taken by the two tennis balls to reach the bottom of the wells. But we don't know the exact times. What we do know is a relation between them. We know that the first ball takes 5 times as long as the second ball. So if the second ball takes a time, say t, whatever that t may be, the first ball will take 5 times as much. So 5 times t. This is very important to be able to solve the problem, to understand how to set up these kinds of relations. Alright, so we know initial velocity, we know acceleration, we know time. We know time as in we know how to relate the times. So we can actually write down a kinematic equation using 3 variables, considering t to be known, and then finding the 4th variable, which is my target, delta y. That kind of equation, if you look at your equations sheet, will be delta y is equal to vi times delta t plus 1/2 a delta t squared. Plugging in information from here, delta y, let's call it y2 in this column, equals vit, this is 0, so that term goes away. This whole term is 0 for this problem. And acceleration is negative 9.8. Negative 9.8 over 2 is negative 4.9. Negative 4.9 times delta t squared. Now delta t is ti is 0 because that's when you drop the ball. So delta t is just t minus 0, which is t squared. So this is y2. Okay, now what is y1? y1 is using the same equation here. y1 is vi times t, which is 0, minus 9.8 over 2, which is minus 4.9, and t squared. In this case, it is t1 squared. t1 is nothing but 5 times of t, so it is actually 4.9 times 5 times of t whole squared. Okay, so we have y1 is equal to minus 4.9 times 25 t squared. Okay, so y1 is minus 4.9 t squared times 25. If you look at y1 is equal minus 4.9 t squared. What is minus 4.9 t squared? Minus 4.9 t squared is equal to y2. So y1 is equal to 25 times y2. Therefore, well 1, the first well, is 25 times deeper than the second well.